Oxidation-reduction reactions, redox for short here. That'll be the topic of this lesson in my high school chemistry playlist. Now, we just finished a lesson on the different types of chemical reactions, and this was one of the ones we brought up, but we're going to bring it up to a little greater detail. And then we'll finally, in the next lesson, spend a little more time talking about double replacement reactions as well. Now, if this is your first time to the channel, my name is Chad, and this channel is just simply dedicated to making science both understandable and enjoyable. Now, this is my high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I put a lesson up. So, oxidation-reduction reactions. Now, we introduced these in the last lesson. We went through all the different types of chemical reactions. Now, this is one of the more important ones. So pretty much they are the principle on which all of your batteries and stuff operate. So every reaction that's going on inside a battery is an oxidation-reduction reaction. Also, the metabolism of your food inside your body and how it releases energy. These are all examples of oxidation-reduction reactions as well. So really super important when it comes to storing energy and releasing energy and things of this sort. So we'll spend a little more time talking about it here, but even this is still going to be somewhat of an introduction. We'll have an entire chapter dedicated to oxidation-reduction reactions toward the end of the entire high school chemistry playlist. Now, as we mentioned in the last lesson, an oxidation-reduction reaction is really just an electron transfer reaction. We have to identify a couple of different terms we use, and that's oxidation and reduction. And we used a couple of mnemonics here to kind of remember that. And so one of them is oil rig, and oxidation is loss of electrons, reduction is gain of electrons. And so the species that transfers the electrons away from itself is getting oxidized, and the species that then receives those electrons is getting reduced. So when we look at it, now, the other mnemonic you might see is Leo the lion says grrr. And I like this one better because you get to say grrr. I also like that it has an E in the mnemonic, and that lets you remember that it's lose electrons oxidation, gain electrons reduction, whereas here there's no E, and you have to remember that it's oxidation is loss of electrons, reduction is gain of electrons. So, but either way, both these are fairly commonly and ubiquitously taught, so super helpful in remembering your definitions of oxidation and reduction. Now, the hallmark then that you've had electrons transferred in your reaction is that you're going to have some of the charges in some of the different species change. We call these charges on the different elements in your reaction oxidation states. So that's the way we look at it. And so in order to figure out that you've had electron transferred, you got to be able to identify that oxidation states have changed, which is a pain in the butt, and I'm sorry. But this means you've got to memorize some rules for how you first figure out what those oxidation states are. So we're just going to begin this part of the lesson by just going through and assigning several species and assigning all the elements of those species their oxidation states. And we'll use those rules that are on the study guide. I'll put them on the screen here somewhere as well. And rule number 1 says if you have an element in its elemental form, it is in the zero oxidation state. So what that means, when you have an element that is all by itself and there's no charge on it listed at all, that's its elemental form. So, and that could be, for most compounds, it's going to be when it's monatomic, like sodium here. This would be the zero oxidation state. But chlorine is one of those 7 diatomics, and again, but it's still just a single element. There's 2 atoms of it, but it's a single element, and there's no charge listed up here. It must be in the zero oxidation state. So, and then for some rare species, they're even triatomic here in the case of ozone. So, but again, it's 3 identical atoms, all the same element. So one single element, no charge listed up here. It must be in the zero oxidation state. So that's rule number 1. And that's not going to be the most common case. So, but we'll have 3 more rules, and they're going to deal with what if you have elements that are charged or in compounds, then how do you figure out their oxidation states? All right, so the next rule we use are for ionic compounds. When you have what are called monatomic ions, we learned about these when we're naming compounds. So monatomic ions, not to be confused with polyatomic ions. So, but when you've got an ionic compound like metal and non-metal here, if you've got monatomic ions, you can usually tell what their charge is going to be, as long as they're not transition anyways, based on where they're located on the periodic table. So in the case of chlorine, chlorine's going to have a -1 oxidation state. So life is good there. Now, if we move on to magnesium, if you look at where he is, he's a group 2 metal, and therefore is typically going to be +2. And so in this case, +2, -1, life is good. Now, what if we'd had a transition metal in there instead, like in CuCl2? So in the case here, copper is one of those transition metals, and you can't just look at the periodic table and figure out what his charge is going to be. It turns out copper is routinely either +1 or +2, but you can't even tell that, what your options are based on where it's located in the periodic table. And so with the transition metals, you've actually got to figure out what their oxidation state is based on what anion they're with. And so once again, the chlorine, so the oxidation state is -1, and it's always defined per atom. So there's 2 chlorines, and there's a total of -2 charge here, but each atom is -1, and that's what the oxidation state identifies. But to balance out the charge then in this ionic compound, that means copper in this case would have to be +2. And so if it's a group 1 or 2 metal, you can figure out what it is just based where it's, where it's located in the periodic table. But if it's one of those transition metals and stuff, then you're going to have to figure out what it is based on context, I like to say, just based on the charge of the anion or the oxidation state of the anion that it is with. Okay, so that's when we're dealing with monatomic ions, but what if we're dealing with either molecular compounds made of all nonmetals or with polyatomic ions, which are also made up of nonmetals? What do you do then? Well, in that case, so you typically follow these rules in order, and you first say, well, is there anybody in their elemental form? Well, if you have a compound, as in the case of either of these, no. Then you skip rule number 1. So then you move on to rule number 2, and you say, well, is it ionic? Because if it's ionic, then do I have any monatomic ions? But what if I've got a compound made up of all nonmetals? Well, then it's not ionic, and that rule is not going to help us. So then you move on to rule number 3, and rule number 3 says, assign the regulars, I'm going to call them. So if you've got a molecular compound, or let's just say you had a polyatomic ion all by itself, like sulfate here. So these are made of all nonmetals either way. And that's when you move on to rule number 3 and you say, okay, assign the regulars first. Well, the regulars are hydrogen, and in a compound full of nonmetals, hydrogen is going to be +1. Now, it turns out hydrogen is not always going to be +1, but when it's mixed with other nonmetals, it's going to be +1. All right. So the other regulars are going to be oxygen, and oxygen is usually going to be -2. So, and then your halogens are usually, as monatomic ions anyways, going to be -1. But if we're not talking about monatomic ions, then that really goes out the window and stuff like this. So, but usually you kind of assign these regulars here. Start with hydrogen, make your way onto oxygen, fluorine, so will always be -1. And then your halogens are usually -1 when they're as monatomic ions, but we already kind of covered that base here as well. So, but after that, you typically are just going to see, okay, who's left after you assign the regulars? And he has to balance out the charge. And so in this case, if you take a look at your hydrogens, we've got 2 hydrogens that are +1 each. That is a total charge of +2. Now, if I said, what's the oxidation state of hydrogen? If you said it's +2, that's wrong. Oxidation state, again, is always defined per atom, and it's just +1, but there is still a total +2 charge here. And then 4 oxygens that are -2 each. Again, the oxidation state is -2, but the total charge on all 4 of those oxygens combined is -8. And we're doing this to figure out, well, then what charge does sulfur have to balance this out? We assigned our regulars. Sulfur is the only one left. He's got to balance this out. And in this case, the overall compound is a neutral compound, so it's got to balance out to 0. So +2 here, -8 here. That sulfur is going to have to be +6 to balance this out. Cool. And this is how you treat both molecular compounds as well as polyatomic ions. Now, in the case of a polyatomic ion, we'd work this, at least in principle, the same way. I'd look for hydrogens, again, all nonmetals, so I'm looking for hydrogens, don't have any. Look for oxygens, he's my next regular, and here he is, so we'll assign him as -2. And the only non-regular I got here is sulfur, and he's just going to have to balance the rest of this out. Now, in this case, though, this is not a neutral compound, so I'm not balancing it out to 0. This overall is an ion with a -2 charge, so I'm going to have to balance it out to get an overall charge of -2. And so once again, you got to remember that we've got 4 oxygens, which gives me a total charge of -8. And the question you have to ask yourself is then, well, what do you have to add to -8 to get a total, not of 0, but to get a total of -2? Now, you could also look at this. Some students struggle with this. You could also look at this as an equation. You could set up as an algebra equation. You could say that whatever sulfur is plus 4 times whatever oxygen is has to add up to the total charge, which in this case is not 0, but -2. And so you'd say sulfur plus 4 times, and we saw that each of those oxygens is -2. And again, adds up to a total of -2. And if you just solve for S here is like it's like X in an algebra equation, you'd find out that sulfur here is going to still have to be +6, pretty much like the example above. Key here again, I just want to give an example of an ion because here the charge isn't balancing out to 0, but charging out to whatever the total charge on the ion, in this case, -2. Cool, but this is the process of assigning oxidation states. So, and this, you want to get fairly good at this so that you can do it quickly. So, because this is going to be the hallmark of how you identify whether or not an oxidation reduction reaction has occurred, is you're going to be looking for changes in these oxidation states as we go from reactants to products. That'll be your evidence that somebody either lost electrons or gained electrons. All right, so the next question on your handout has this lovely reaction listed, and this is a common reaction occurring in one of your everyday common use batteries. In this case, it's having you identify the species that get oxidized and reduced. Now, in an oxidation reduction reaction, if I'm asking you to identify somebody that gets oxidized or reduced, they're always going to be on the reactant side, never on the product side. So the species that get oxidized and reduced, always reactants. So, and you're going to figure it out based on changing oxidation states. So what we want to do is go through and assign all the different oxidation states here and figure out who changed. Now the first one here, zinc, he's easy because he's just a single element with no charge listed. He's an element in his elemental form, rule number 1, and he's simply in the 0 oxidation state. Now everything else is part of a compound, so he's the only 0 oxidation state we should anticipate finding here. Now, if we move on to the next one here, this is an ionic compound, metal and nonmetal, and manganese is a transition metal. He shows up in the middle of the table, and we'll have to figure him out based on context. You can't tell what his oxidation state or charge is based on just where he is on the periodic table. So, but oxygen as a monatomic ion is going to be -2. And if he's -2 and there's 2 of them, then manganese here is going to have to be +4. Cool, move on to the product side and do the same thing. And here is zinc and oxygen. And once again, zinc, it turns out, is always +2 as an ion. Again, it could be in its elemental form, but as a part of a compound, it's always going to be +2, it turns out. So we learned that when we learned how to name compounds. So, but we might have figured them out based on context, because oxygen has to be -2, which would force zinc to be +2 anyway. So if you remembered from naming compounds that zinc always had to be +2 as part of an ionic compound, great, but we could still figure it out on context here as well. And then finally, once again, manganese, we got to figure out in context as part of this ionic compound. So we'll assign oxygen first as -2. And with 3 oxygens that are -2 each, that's a total of -6. So the manganeses are going to have to total out to +6 to balance it out to neutral. And with 2 manganese atoms there, ions in this case, that means they're each going to be +3. Okay, so now we want to look at the changing oxidation states to see who got oxidized and who got reduced. And I want to start with reduced. Now, if I told you that my height got reduced, that means I got shorter and shorter and shorter. So my height goes down. And the reason I bring that up is because that's the way they name reduced. When you get reduced, it's because your oxidation state went down. Now, if we start with zinc, zinc goes from 0 to +2. That's not going down, that's going up. So, but manganese, on the other hand, is going from +4 to +3, and then oxygen's just staying the same, -2, -2, -2. So oxygen's not getting oxidized or reduced, but it's manganese that is going down. And so in this case, we would say that manganese over here got reduced. And it's the reactant here where manganese gets reduced. And we could say this 2 ways. We could say that manganese is the element that got reduced, or we could list the entire chemical species on the reactant side that it's a part of that got reduced. So whether you say manganese got reduced or MnO2 got reduced, those are both accurate statements. All right, now if you call reduction is the gain of electrons, and so to go from +4 down to +3, you must have gained negative charges. And that's the tricky part, because we're talking about the transfer of negative charges. Well, you know, if we were transferring money, well, when you gain money, your value goes up. And when you lose money, your value goes down. But when you gain electrons, because they're negative, your charge goes down. And when you lose electrons, your charge or oxidation state goes up. And it seems a little bit backwards. And that's why I wanted to focus on the reason they call it being reduced is because your oxidation state goes down. So just as a quick way to remember how to identify this quickly, because it really is something that is very easy to get backwards in your head. All right, so manganese is getting reduced, but zinc here, on the other hand, is going from 0 up to +2. And if you're getting more positive, it's not because you gained positive charges. Again, the key is you lost electrons, you lost negative charges. And so you got oxidized. And whether we want to say that zinc got oxidized or zinc solid, if we list the whole chemical species, it is the whole chemical species, got oxidized, same diff. So, but is zinc got oxidized? Not in ZNO. Again, it's never the products that got oxidized or reduced. It's always the reactants. So now we just want to take a couple of minutes and talk a little more about single replacement reactions, the reactions we introduced in the last lesson. And again, these are a type of oxidation reduction reaction, so the context here. Now, I've got a couple here, and I've given you this activity series, and then I've got this lovely statement down below that I'm sure you've already noticed. And unfortunately, this statement right here is not true. So just because I write something on the board, I could have said Chad is the best looking man alive, just because I write something on the board doesn't make it true. Now, obviously there's a point to this. This is not just nonsense. But when I write a single replacement reaction, just because you can write it on the board here doesn't mean it's actually going to happen. So it turns out reactions typically happen in one direction or another, and either they go in the forward direction or they go in the reverse direction. So one or the other, and just because I write it this way doesn't mean it's actually going to happen. And that's the purpose of an activity series. An activity series is something provided for you. It's not something we force you to memorize, but when it's provided, it is a tool to help you predict when single replacement reactions will happen and when they don't. And the word we use for a reaction that happens is spontaneous. So if I say it is spontaneous for this marker to fall to the ground, that's a true statement. Now, if I say it is spontaneous for this marker when I release it to fly up to the ceiling, that is not a true statement. So we know what spontaneous means. It's things that happen unaided, whereas non-spontaneous are things that don't happen unaided. So in this case, the way it works with that activity series is when you look at the single replacement reaction, the species that is doing the replacing has to be higher on the list. Now, I like to think that this activity series is just a list of the best looking metals, and the best looking ones are at the top of the list. And so in this case, zinc and nitrate, they're a couple. And if copper wants to replace zinc and be a couple with nitrate, leaving zinc all alone, then copper better be better looking than zinc for that to happen. And when I look at the list, though, if we take a look, so I see copper way down here, and zinc is right here. And it looks like zinc is actually the better looking metal. So as a result, this reaction is not going to happen. Copper is not going to be able to replace or displace zinc in zinc nitrate. And so this reaction, we would say, is not spontaneous. So it turns out it is the reverse reaction that would be spontaneous. For the reverse reaction, you'd see that zinc would have to be replacing copper, and that's exactly what could happen. So by figuring out that it's non-spontaneous in the forward reaction, we'd actually figure out that it's the reverse reaction that would be spontaneous. So that's the use of this activity series. Now, what's really happening here, obviously this is not a list of the best looking metals, but it is a list as you go up of more easily oxidized metals. Now, again, single replacement's an example of a redox reaction, and so you have one species getting oxidized and one species that's getting reduced. Well, the species that's getting oxidized better be the one that is more easily oxidized for it to be spontaneous. And so in our case, if we take a look and assign oxidation states, we can see here that copper is an element in its elemental form is 0. Over here, it's paired with nitrate, which is -1 each as a polyatomic ion. So copper here would be +2. And then going from 0 to +2, he's going up, not going down. He's losing electrons, and we'd say that copper is being oxidized. On the other hand, here zinc is +2 and ends up in its elemental form at 0. And so zinc is actually going down from +2 to 0 because he's gaining electrons. And so in this case, he's being reduced. And so you focus on that one being oxidized, and the real rule with the activity series says that the species being oxidized has to be the one that is more easily oxidized, has to be the one that's higher on the activity series. And in our case, copper, the one that was being oxidized, was not higher on the list. That's why it was not spontaneous. If we look at another example here, so here again, I like to think of it, well, hydrogen and chlorine, they're a couple. And if magnesium wants to end up being part of the couple with chlorine and leave hydrogen all alone, well, then magnesium better be better looking than hydrogen. And so once again, we'll take a look at the comparison between magnesium and hydrogen. And hydrogen's right here. Magnesium, on the other hand, is way up here. And magnesium is better looking. And so this reaction will totally be spontaneous. It will actually happen. And again, the way we should have really approached this, though, should have said that, magnesium starts out 0 oxidation state, ends up in the +2 oxidation state. That means magnesium is the species being oxidized. And I could figure out that, yep, hydrogen's going from +1 to its elemental form of 0 and it's being reduced. But the key is I don't really have to worry about who gets reduced. I just got to worry about who's getting oxidized, because they're the one who has to be higher on the higher on the activity series, the one that's more easily oxidized. And in this case, magnesium compared to hydrogen, yep, magnesium is definitely higher on the list than hydrogen. This reaction would be spontaneous. And so if we kind of look, again, in a more physical fashion of what spontaneous versus non-spontaneous means, if you drop a piece of magnesium into an aqueous solution of hydrochloric acid, that magnesium will dissolve away, becoming part of an aqueous salt here, and hydrogen gas would bubble out of the solution. You'd see bubbles coming out. Cool, it's spontaneous. To contrast that, though, if you drop a solid copper in an aqueous solution of zinc nitrate, it sinks to the bottom and it sits there and nothing happens because it is not spontaneous. Cool. Hopefully now you know how to use that activity series. And once again, you don't have to memorize that activity series. If we want you to be able to predict whether or not a single replacement reaction happens, we will provide you with an activity series, whether that be on the test or just give it to you on an appendix on a table somewhere at the back of the test, or give your open book test or something like that. But you should know that's the purpose of that activity series. Now, if you found this lesson helpful, consider giving me a like and a share. Pretty much the best things you can do to support the channel. And if you're looking for the study guide that goes with this lesson, or if you're looking for practice problems, check out my premium course on chadsprep.com.